All right, in the last video, we looked at the create target component. I showed you how we can, with a right click, add more inputs to our robot targets to further define the motion, such as the configuration, the speed, as well as the zone and many other parameters that we can add to a robot target. In this video, we will have a specific look at the tool parameter that defines the tool and also the offset of the TCP that we have from the robot flange. I hope I can explain how this all comes together and why this is necessary in our robot program in this video. Whenever we're using universal robots or any kind of industrial robot, the robot itself is just a motion platform. The robot itself doesn't have any functionality, and the functionality comes from whatever tool we add to the robot. This might be a gripper, this might be a nozzle of some sort to extrude, this might be a drill or a milling spindle to cut something, and whatever we add to the robot that then gives us the functionality. In order to create the tool, first off, I will just simply clean up a bit. With a right click, I will remove some of the inputs that we don't need from the create target component until we only have configuration, the motion type, and the tool input. So the first thing that I will do is to go into the tab for the robot plugin and get a tool parameter. This tool parameter component doesn't do anything by itself, but it's a good way of keeping our definitions clean. Next, I will go into components and use the create tool component. First thing to do is to give the tool a name. For that, I will use a panel, and in this case, I will just call it tool_01. Make sure whenever you're naming the tool that the tool name does not have any special characters, and it should also not have any spaces. You will also get an error for that, and also make sure that you don't start your tool name with a number or any kind of special character. The reason for that is that this tool name is also put into the robot program, the code that is sent to the robot, and if it's in a certain format that the robot doesn't recognize, then it won't work. And in case with universal robots, we unfortunately don't even get an error message. We just send the program and nothing happens. The next thing that we can set is the TCP, and as you can see, for now this is set to the world XY plane. So as you know, the world XY plane is simply the plane that is at the origin of our Rhino 3D view, so at coordinate 0, 0, 0. And what this does, what this TCP, the tool center point, does, is to define an offset from the robot flange. And this offset is defined in relation to this origin. So if, for example, I have a tool attached to the robot that is 10 centimeters long, let me add the robot back in here. So I have a tool attached here that is 10 centimeters long. I will need to create an offset from this origin point of 10 centimeters. So in this case, I will do this by creating a point with the construct point and simply do 100 millimeters in Z direction. And now you can see that this plane is offset in Z direction by 100 millimeters. What this does then is to make sure that this robot, instead of before, the robot simply had the flange basically touch each of these waypoints that we defined. So let me show you what it did before. I will disconnect the tool, and you can see that these three planes that we defined as our robot waypoints, the robot basically touches them directly with its flange because there was no offset. And now that we have this offset, you can immediately see how the robot is now has this 10 centimeter offset. So if it would have some sort of tool that is attached to it with this length, now it still reaches each of these points, not with its flange, but with the tool that is attached to it. We can also define rotations by using the TCP plane. So for example, we might have a tool that does not that is not used just vertically on each coordinate, but instead is has a certain angle to it, and I will quickly show this with an YZ plane. And if we use this one, let me show you here. So this is a plane that is instead of being horizontal, it's vertical in relation to the origin or the world XY axis, and this then also has an effect on the orientation of the robot. So we did not change the orientation of the planes, of the waypoint planes. In fact, we only changed the orientation of our tool center point. I will undo this and go back to this XY plane for now, and we will look at the other inputs to the create tool component. The next thing is something that is quite advanced. It's the calibration. We don't need to use this, but this is one way of actually calibrating a TCP. So in this case, we had we simply said, okay, 100 millimeters in Z direction was our new coordinate, but we can also do this by basically inputting 4 points, basically flange orientations that then can convert it into one TCP. This might be a bit confusing. I might do another video on this if you're interested, but for now we will not use this input. The next thing is the tool weight, and this is quite important, especially for universal robots, since they are collaborative and they go into protective stop if the torque and forces on the robot exceed certain limits, and so the robot needs to know how heavy the tool is. Otherwise, it might think that it hit something, but in fact it was just the weight of the tool that was exerting certain forces. This weight is given in kilograms, so in this case 0.1 is just 100 grams, which is enough. The next thing is a center of mass. We don't have to add this center of mass. However, especially if you have a tool that is quite heavy and or that has a weight that is not in the center but more at an off axis, or at a that is not really in the center but instead offset. We can also set this center of mass so the robot kind of can calculate what kind of forces it has to expect when doing certain motions. And the last thing is a tool mesh. And of course, we don't just want to set the offset, but we also want to know, or we want to have a visualization of whatever is attached to the robot. This mesh can be input either from any geometry that we create in Grasshopper. So let me quickly add a cone here. So this is the base. The radius could be, for example, 30 millimeters, and for the length we will also use the height that we created here, and this cone can be put directly into the mesh input, and now we can see that this cone that we created, that is located here on the origin, is now attached to the robot, and the TCP is basically perfectly at the tip of this cone. A very simple representation of the tool might be enough if we have a very simple tool, but of course most often then it's something more complex. Maybe it's a gripper or some sort of extrusion nozzle, and then we might even have a 3D model of whatever tool we have attached to the robot, and we actually want to insert this 3D model. To do this, we simply import whatever kind of geometry we have into Rhino. In this case, I basically just added this 3D model, which is a tool that we use in some workshops. It's basically just something that we can then attach further objects to. But just to show you how we can import this is pretty straightforward. The same way we import any kind of geometry into Grasshopper. We simply have this tool as an object in Rhino, get a mesh parameter in Grasshopper, set one mesh, select the mesh that we have in Rhino, and now we have this mesh attached to our robot. And here you can see that this tool, for example, is a bit off axis. So in this case, our TCP would not just be offset in the direction of in Z direction, so not just away from the flange, but also in other directions. And let me check if I can quickly do this. This is the wrong one. But we want to make sure that we are actually, that we actually have the actual point of the tool that we want to the point of the tool that we want to touch the coordinate, or that we want to get to the coordinates, the waypoints that we defined, that this is our TCP. And we can see that here, this is our tool, and this is our TCP. We can also, instead of constructing this point in Grasshopper, of course, we can also create a point in Rhino. And reference this point as our TCP. And now if we would change this, this would also change the TCP of the robot. So this is basically the way we can define this TCP in a different way. Instead of constructing a point in Grasshopper, we can also just construct a point and make it in relation to whatever tool geometry we have, and then add it to the robot. All right, that is basically it for tool creation. So to recap, we create a tool that is part of the create target component, and each tool has a name, and the most important thing about the tool is the TCP, so the offset that we give it, that is then transferred to each robot motion. We can add a calibration, but we don't have to. We can calibrate this way, create the TCP in a different way. Instead of giving it a point, we can use this calibration, but for now I have not run into a situation where this was very useful. But we should give a tool weight. We can give a center of mass if that is necessary, but what is very important is to use a mesh, some sort of geometry, to kind of visualize our tool so that we can make sure it is in the right orientation, in the right direction, and we can then also see how the tool might interact with whatever geometry we want the robot to move to. All right, in the next video, we will look at other ways of using geometry to create robot targets. Before we go there, I will simply clean up this way we created our tools, just to make everything just slightly nicer. So this is a group for our tool creation, and I will call it tool creation, and the rest of the definition stays the same way. All right, see you in the next video.